Hi, I'm Reuth Mirsky. I come from UT, and I'm very excited to be here today and to tell you about my research and my vision to build a seeing-eye robot for people with visual impairment. As David said in his introduction, while AI have reached some great accomplishment lately, we still can't say that AI is a solved problem. A few examples of that. On the left here, you can see Atlas, which is Boston Dynamics' famous bipedal robot. When it accidentally dropped the box, as you can see here, it reaches an unknown state and simply loses it as it's off its policy. You can see it just collapses. It doesn't know what to do, just falls down. Also, we recently seen a successful wolf or dog classifier that was able to differentiate huskies from wolves, which sounds very impressive until it was discovered that it relied on the background instead of on the animal itself. And wolves are much more prevalent in snowy backgrounds, while huskies are prevalent on floors and carpets. And finally, the glorified GPT-3 that everyone's talking about, it extincting human literature and poetry. As a new research, you need to write a research statement describing your research vision. So I gave GPT-3 my research statement to complete. I am interested in similarities and differences between artificial intelligence and natural intelligence, and how the gaps between the two can be narrowed in order to design systems and robots that are capable of doing some things, is how it chose to complete it. Not exactly solved problem yet, but when it works very well. The successes of modern AI are unquestionable. For example, using motor primitives, robots can learn complex motor tasks. We use attention mechanisms to train vision and NLP systems. And using theory of mind, Google can predict that on a specific day, we're interested in a soccer game and the current result of Real Madrid, rather than stating our emotional state of being real mad. So the difference between the former slide and this one is that these works were inspired by human or other natural cognition and human physiology. Their successes are based on human abilities. This is human motor learning and how people learn, how people focus their attention, and the ability of people to perceive other agents and people's mental models. So now in the correct version, I'm interested in similarities and differences between artificial intelligence and natural intelligence, and how the gaps between the two can be narrowed in order to design systems and robots that are better collaborators and which can be useful true allies of humans. And to accomplish that, I'm taking as an inspiration one of our best collaborators, a dog, and more specifically the seeing-eye dog. These are dogs that are trained to lead blind and visually impaired people around obstacles. They're unique in being the only service dog that is not just trained on obeying its owner, but also on intelligent disobedience. If they're given an unsafe cue from their handler, they are taught to disobey it. This understanding makes them a very intelligent collaborator. If you think for a second about this achievement, the dog who usually does obey needs to understand both a specific context and the state that are so unsafe that it should not obey its owner or even force action on them. So the question is, what does it take to create something so intelligent as a seeing-eye dog that can perform impressive feats such as intelligent disobedience? So first, it needs to understand that different agents might have different goals and plans and recognize them on the fly. But this is not enough. It also needs to be a good collaborator. And for that, it needs to act properly when plans derail from track. So the seeing-eye dog needs to first reason about the goals of its teammates and then react to them and sometimes replan accordingly if something goes unexpectedly. Also, one more thing that we need to consider is a person that gets a new robot. This new robot should be able to teach its new owner about its abilities and limitations and adapt its own policy to the owner's learning curve. Some people are slower learners or faster learners. We want to be able to adapt to that. And moreover, as a team, they will also need to adapt quickly to new situations, even if they're in a state that they have never seen before. If you remember Atlas dropping the box, this is something we don't want such a mistake with a seeing-eye dog or a seeing-eye robot. And lastly, in order to create an agent that can act as a guide dog that disobeys when needed, and not just be a passive white cane that beeps when something goes wrong. If you remember Samantha mentioning alarm fatigue, we don't want something that people can just ignore. So we want to have the robot embodied. We'd like to have the agent embodied in a robot, and it should be able to interact with a human in a sociable manner. So this list does not cover all the intelligence and social requirements of a seeing-eye dog, but it represents a comprehensive set of tools which I utilize in my research so far. Planning and reasoning algorithms for multi-agent systems, and investigation of nonverbal communication cue in human-robot interactions, and reinforcement learning models. So there's a lot of different things that I want to talk about today, and I decided instead of diving into just one of these, just give you a very quick overview on each of these. But if you're interested in learning more, please feel free to contact me after this talk. I'll be happy to talk more. So I will start with plan recognition using my work on extending a plan recognizer with a communication channel. So first, plan recognition is a fundamental AI problem that was formally defined in 1986 by Henry Kotz and James Allen as the challenge to infer the plan of an agent given observations and a database of recipes. So if I see my husband in the kitchen melting chocolate and breaking some eggs, and I know that all of the recipes he can make is from a specific recipe books that he likes, I can infer that what he's doing now is making us a chocolate babka. Specifically in my research, I focus on plan recognition that relies on plan libraries and not recipe books. This means that my inputs are, again, a sequence of observations and a recipe set that is represented as a grammar. And so you can see here, for example, that we always have a root that is a start of a sentence in a sense, and the words that we observe in that sentence are the actions that the agents can take. Boil water, add a pasta, and make sauce, and so on and so forth. So with these inputs, I process the plan recognizer process these observations and outputs a set of trees such that each root of the tree represents a goal. And so here, for example, we have two goals. In this, we have two plans, one for making pasta, one for making a chocolate cake. And this is an example of one hypothesis. In this hypothesis, we hypothesize that the actor is making two dishes. So we have two goals in the same hypothesis. And when we work with a plan recognizer, we get a set of such hypotheses. So again, this is very time consuming and can confuse the observer even more than being helpful, given that we get these many observations. So the main challenge in using this approach is how to disambiguate between the different hypotheses. So if you notice both, if you do plan recognition like this, but also in the general formulation that I gave earlier, we perform what is called keyhole recognition, meaning that the actor and the observer don't try to communicate between them, even when such an interaction can be beneficial and help us discard some of the redundant hypotheses. At no point here do you see that the observer can stop the actor and say, are you trying to make pasta, for example? So to overcome this gap, in my work, I was interested in designing a framework that considers communication in the context of a plan recognition problem in the final goal to reduce ambiguity, with the final goal to reduce ambiguity. So Now the plan recognition task becomes to infer the plan of the agent given observations, a database of recipes, and also the ability to query the actor. However, I don't know how many of you are familiar with Clippy, but when you ask someone to what their goal is or goals too many times, it can become cumbersome. So we want to find a way to minimize the number of questions we ask. So to approach this challenge, I designed a framework to reason about queries in the plan recognition process, which is called Sequential Plan Recognition, inspired from the world of sequential diagnosis. And in SPR, Sequential Plan Recognition, you can take any plan recognizer that uses plan libraries and augment it with the ability to query the other agent. So the main novelty of SPR is by removing the keyhole assumption, and it was designed to reduce interruptions, and it was also proven to be sound and complete. So I won't go into many details, just an overview of what SPR does. It starts with any plan recognizer that outputs a set of hypotheses. We then choose one tree that can be a component of one or more hypotheses, and we ask the actor, is this tree part of your plan? So if you remember, we can have more than one tree in a plan, so we ask about only one of these trees in the hypotheses. And given the answer, is this part of what you're doing, we either get a yes or a no, and we need to update this set of hypotheses, and the process can start over. And there are, in this process, there are three main challenges. First is when to stop the recognizer from processing observation and choose to query, because these are two different ways that we can gain information. One is by observing, one is by asking, and we want to balance between the two and decide when to use which. The second question is what to ask to maximize our knowledge gain, basically. And the third question is, given the answer, how to update the hypothesis set. And I won't go into the details, but it's not a straight yes or no. If someone tells me, no, this is not part of my plan, that I can discard all hypotheses that contain this plan, because it might be that this plan will extend into a different plan that is part of what the actor is doing. So you need to be careful about exactly how you update the hypothesis set. This is basically about SPR, but since I want to talk about other projects and interesting things that I do, I will go to the next section. So far, I've been talking about adding queries to goal recognition, and now I want to extend that to queries in the context of ad hoc teamwork. So ad hoc teamwork is a bit more complex task than just recognition. It has two stages because it needs to create an autonomous agent that is able to efficiently and robustly collaborate with previously unknown teammates on tasks to which they are all individually capable of contributing as team members. So if you think of an example of a search and rescue party that needs to team up with other party from a different country, or even if you play soccer with new players you've never played with before. In ad hoc teamwork, you have this stage of recognizing the goals and abilities of the agents that you work with, and then you need to plan accordingly. So there are two steps here, both recognition and acting. However, just like we had in the plan recognition domain, most works in this topic also took the assumption of no pre-coordination, a type of keyhole, a step further. And they also assume that even once the agent meet, they don't communicate and don't try to inform one another. So again, this assumption is very restrictive. And the fact that we did not communicate with someone in the past doesn't mean that we can't communicate with them now. We as humans are able to talk with new individuals once we meet them. We use existing communication channels, we can learn new communication channels, and we can teach other teachable agents. So for example, in the drop-in soccer example, even if I never met the players before, we might be able to talk. I speak Hebrew and English, so we might talk in one of these languages. And even if not, we might wave to one another. We might construct some sign language between us that will work for both of us. So all of these types of trying to communicate, we defined as a new problem called communication in ad hoc teamwork. So if you consider a service robot that is deployed in a hospital during a crisis, and it can assist the staff by fetching required resources from a medical cabinet, this robot might not be familiar with the changing staff and might have never worked with some specific people in the past. But that doesn't mean that it can't communicate with them once it is deployed, and it can thus become a better team member. And again, we don't want the robot to just ask every physician or nurse it sees, what do you want me to do now? As explaining this to the robot will be cumbersome and will cause unwanted interruptions. So this is the other side of what Samantha talked about in terms of interrupting to give information. This is interrupting to gain information from another teammate. But just like it happened in Samantha's work, here as well, you don't want to overload the other agents. So instead, we want to think of a way to reason about when to interrupt someone and what information do we want to get from them. So this scenario was the inspiration to identify a subset of problems within the realm of communication in ad hoc teamwork. In these specific problems, we have two agents. The ad hoc agent that we design and can query its teammates about its goals in order to be a useful team member. So in this grid world on the right, for example, we have two agents, a physician and a robot. The physician might be planning on visiting a patient in one of the colored rooms that you see here. And the robot can assist by fetching the proper medicine for that patient from the medical cabinet on the right. If there is some ambiguity about the physician's goal, for example, if she's heading to one of the upper rooms, the robot can ask, what are you going to the green room? And this is a very specific example. It's a part of a wider set of CAT problems, and we named all these problems that have this ability to query a limited number of times in a multi-agent systems environment in ad hoc teamwork as sequential one-shot multi-agent limited inquiry for communication in ad hoc teamwork, or in short, SOMALI CAT. So this work has been published last year and we're still working on this. So a lot of exciting new stuff is going on. And again, I don't have time to go over everything. I'll just give you some brief introduction to what is the type of reasoning we do in CAT. So intuitively, we take into account two things. First, we need to choose to query when there is some uncertainty about the physician's goal. So, for example, in this grid world, if the physician starts walking north, we'll have to wait for her to turn either to the yellow or the green room, which on the worst case can take up to 9 time steps. So we call the time until it's clear what the physician's goal is as the zone of information. It represents the worst case plan of the physician until we have the information we need to distinguish between the goals. So in this case, this means that our zone of information are time steps 1 through 9. Beyond that, it's not beneficial to query anyway because there is no ambiguity about the goal of the other agent. Assuming that they're acting optimally. By the way, this is a tricky point, and we extended that in our successive work, but I'm not going to talk about that today. And on the other hand, so we talked about the upper bound of when we might want to query. On the other hand, we don't want to query too soon. We don't want to query before the robot needs to commit to a specific goal. So for example, if all of the resources that the robot can fetch are in the same medical cabinet, it can wait before it queries until the 6th, 9th step when it actually needs to pick up something, and only then it should interact with its teammate if there is still some ambiguity. So we call this time until the robot's optimal actions to different goals are distinct as the zone of plan branching, which is when the plans branch. And in this case, it means time step 6 and beyond that. Because as I said, the 6-9 step is when it will pick up something from the medical cabinet. And if it picks up the wrong one, it will have to backtrack. So together, zone of information and zone of plan branching are combined to give us the zone of querying. It is the intersection between these two zones. And it basically gives us the time steps in which there might be a positive gain from querying about the physician's goal and a potential goal from not querying. So in this example, the zone of querying are time steps 6 through 9. And this is when, in this whole potential set of plans, the time steps in which querying should even be considered. Outside of that, it would just be a waste of time to try to reason about whether we should query or not, because the answer is no. As I said, the zones only work if you assume that all goals are as likely, for example, and that the agent is optimal. So if you think of a case where the patient in the green room is about to go home and the monitor in the yellow room starts to beep intensively, in this case, the fact that the worst case is that the physician would go then and then turn right or left is less beneficial for us. It makes more sense to estimate that with higher probability, the physician will go to the yellow room. And then we might not want to query, even though, even when we do enter the zone of querying. So this is a work that we've extended as well, and I'll be happy to talk more offline if anyone is interested in that. So far, I discussed how a single robot will need to reason and act as part of a team, especially with respect to the question of when it should stop its planned execution and communicate with its owner to better understand their goal or policy. Next, I want to talk about something slightly different. I want you to think about a blind person who gets this cute dog for the first time. Usually they get them when they're a year older. This is a small puppy. They are going through training, but once the blind person gets this dog, it's not an exciting time usually. In a discussion I had with a single dog trainer, he told me that some of the people he worked with say that when their old dog retires and they get a new dog, it's like losing their eyesight all over again, because the new dog still doesn't know the nuances of working with them. And they need to experience this painful transition every 7 years on average, because this is the time that a single dog usually can work. So I would like to avoid this transition crisis with the robotic guide, because it will need new hardware or software, probably more than every 7 years. So we want to find a way to do that more smoothly. And for that, I'm taking part in a project where we use a rehabilitation robot as a teacher, and our goal is to reduce the time until a motor skill is acquired. So this is a joint project with the Renew Lab. It's a mechanical engineering lab at UT, led by Ashish Deshpande. And what we aim to do there is to use robotic training to enhance motor learning, first in healthy subjects, and then once we have a better understanding of the task, to transfer that to impaired populations. So one example of a motor task is serving in tennis. Most professional tennis players use an overhand serve, which you can see in the GIF. But anyone who has learned to play tennis a bit knows that it isn't as simple as picking up the ball, flinging it in the air, and aiming. And it takes a while to master a skill like playing tennis, or another, for example, playing a piano. And there is a known magic number that people consider as a common rule of thumb for the number of hours that you need to invest to master a skill, which is 10,000 hours. In realities, if you're familiar with the sentence, all models are wrong, some are beneficial or useful. In this case, again, it's not exactly 1,000, it can be 8,000, it can be 12,000, and it depends a lot on the skill type. But one of the most critical things that will determine how much time we will need to invest to learn a skill is the quality of the tasks that we're training on. This can have a significant impact on the learning. So what I'm working on in this project is to see if we can construct an efficient curriculum that will help us master a skill faster. So in this video, you can see an example of such a motor skill that we wish to train people using the Harmony exoskeleton, which you can see here on the left. And we use Harmony as a rehabilitation robot, and we wish to teach people to play kendama, the game on the right, where the goal is to put the ball in the cup. You will see that in a second, I hope. Yeah, this is what you're trying to accomplish eventually. Now, this student has played kendama before and is very skillful, and we wish to investigate methods in which a new person who never played this game before can accomplish the target task as fast as possible. We want to do that with as little training as possible and improving the quality of the tasks that we give the person. But as computer scientists, we're used to learning machines, not learning people. And we teach machines, we don't teach people. And there are some critical differences between the two. The first one is, while it's easy to see the skill level of a reinforcement learning agent, for example, or an artificial agent, just by looking into its brain, its policy, its parameters, we can't do that with people. We can't really know what's going on inside their brains. And second, we don't have a mapping of how transfer will happen from one source task to another. So for example, if someone has mastered underhand serve in tennis, and now it tries to learn the overhand, does the underhand serve knowledge helps to learn, or maybe it's even cancel, and they cancel each other out? And third, with an artificial agent, it's easy to evaluate its current skill state by just turning off the learning component and just activating testing mode. In people, we can't do that. Every test that we would give the person will still be part of the curriculum that we are giving them. So we have to take that into consideration. So again, I want to have some time to talk about my last project. I will just mention that due to COVID-related restrictions, the robotics world had to undergo some changes in the types of experiments we can run. And we translated the kendama task into this one, which is called Rich Ninja. And this is a really cool game, and if anyone is interested, I'll share the link for it, and you can play that at home with your own webcam. I'll just mention that the dog that you've seen through the presentation is called Tag, who retired from being a Singai dog in Israel 2 years ago. I was his puppy raiser when I was an undergraduate, and from the age of 1 month to 1 year and 1 month. And then he was old enough and started his training as a Singai dog. He's basically how this research idea was born, and I believe that this experience, along with others in the research projects I was involved in, placed me in a unique position to promote this Singai Robot Grand Challenge. And I hope that you can find such motivations and experiences that will determine the type of research that you're interested in. And I look to work with all of you in the future. If you're interested, again, I'll be very happy to talk more offline. Thank you.